and thank you for standing by. All participants will be able to listen only until the question and answer portion of today's conference. At that time, please press star 1. Today's conference is being recorded. If you have any objections, please disconnect at this time. I would now like to turn your conference over to Gina Anderson from NASA Office of Communications. Thank you. You may begin.
Thanks, Julie. Good afternoon. I'm Gina Anderson from NASA's Office of Communications. Thank you for joining us today to talk with experts about science investigations launching on Northrop Grumman's 17th commercial resupply mission for the agency to the International Space Station. Northrop Grumman is targeting 12:40 p.m. Eastern on Saturday, February 19th for the launch of the Cygnus spacecraft atop an Antares rocket from the Mid-Atlantic Regional Spaceport at NASA's Wallops Flight Facility on Wallops Island, Virginia. Here to talk with us about some research launching aboard Cygnus are Jennifer Buckley, Deputy Chief Scientist for the International Space Station Program, who will discuss the breadth of research being done aboard the orbiting laboratory. Scott Robinson, President and Chief Science Officer of MicroQuinn and Principal Investigator for the MicroQuinn 3D Tumor Investigation, a study that examines the effects of a therapeutic on breast and prostate cancer cells. Kevin Takata, Principal Investigator for the Hydrogen Sensor Technology Demonstration, which will test new sensors for the space station's oxygen generation system. Leah Arvani-Titidou, Vice President of Global Personal Care and Skin Health R&D at Colgate-Palmolive, will discuss the Colgate Skin Aging Investigation. Hidetake Okamoto, Assistant Manager of Sales and Planning at the Development Headquarters of Hitachi Zosen Corporation and Principal Investigator for the Space Demonstration for All Solid-State Li-ion Battery Investigations, which will demonstrate a lithium-ion secondary battery capable of safe, stable operation under extreme temperatures and in a vacuum environment. And finally, we'll have Bob Morrow, Principal Investigator for the Exposed Root On-Orbit Test System, XROOTS investigation, a system that will test hydroponic and aeroponic techniques for plant growth and allow scientists to observe root growth through video and still images. Our speakers will provide a brief overview of their research, and we will open the lines for a few questions from reporters after each speaker. Of course, if you're listening live, you can submit questions for our speakers using the hashtag AskNASA on social media at any time. Reporters, your phones are on mute now. To get into the question queue, you can press star 1 on your phone at any time. We'll call on you, and the operator will open your mic so you can ask your question. We ask that you please stick to one question. If time allows, reporters should feel free to ask follow-up. About 1 hour after we conclude, you can listen to a replay of this teleconference by dialing toll-free 866-453-1997 or by visiting the NASA Videos YouTube channel. Again, that number is 866-453-1997. To start, we'll hear from Jennifer Buckley, Deputy Chief Scientist for the International Space Station Program at NASA's Johnson Space Center in Houston. Over to you, Jennifer.
Thank you, Gina. Good afternoon, and thank you for joining us today. It's our pleasure to share with you the science that will be launched on the Northrop Grumman spacecraft on February 19th. The spacecraft is named the SS Piers Sellers. For this mission, the Cygnus spacecraft accommodates a variety of scientific payloads within its pressurized capsule as well as on external sites. This launch, Cygnus will bring up hardware and samples to enable nearly 40 investigations for NASA, the U.S. National Lab, and our international partners. This totals to just under 2,000 pounds of science, technology demonstration, and utilization payloads. NG-17 enables 248 hours of research time for the crew, of which 107 hours are enabled right away upon berthing. I'd like to take a moment to talk a little bit about big picture ISS research. The International Space Station is an incredibly capable and versatile lab. Our focus research areas include human research, biology and biotechnology, earth and space science, physical science, technology development, and education. Over the course of a year, there are hundreds of experiments that are being performed on the International Space Station. Across our international partnerships, nearly 3,000 investigations have been performed on ISS to date. That represents over 4,000 scientists worldwide and over 100 countries globally. Research from these investigations will help us advance in areas critical to our future exploration programs, as well as contribute to improving life here on Earth. If you'd like to learn more about how ISS research benefits life on Earth, the ISS Partnership publishes Benefits for Humanity, which can be found at www.nasa.gov/stationbenefits. Our fourth edition is due out this summer, so keep an eye out for that. Meanwhile, on ISS, we currently have 7 crew members living aboard, and NG-17 kicks off a very busy and exciting spring. In just 4 months, we'll have 2 cargo resupply missions carrying experiments and facilities that will continue the orbiting laboratory's contributions to improving life on Earth and pushing us farther into deep space. Following NG-17, Axiom will be launching AX-1, our first private astronaut mission, or PAM mission, to ISS. And this spring will also see the launch of Crew 4, who will conduct 200 to 300 investigations during their expedition. At the end of March, we'll welcome NASA astronaut Mark Vande Hei home from his nearly year-long mission aboard the International Space Station. He's set to break the record for the longest continuous presence in space by a U.S. crew member. What we're learning from the opportunity for extended human research in microgravity will help us keep astronauts safer in future missions. We should also see the launches of Boeing OFT-2 and Artemis 1 coming up late spring. In just a moment, you'll hear directly from the researchers whose science is performed on ISS. For more than 20 years, we have been testing technologies critical for deep space exploration. We've grown our understanding of how human bodies react to life in microgravity and strengthen the international partnerships that allow these missions to thrive. These investigations and all of the science hardware launching on NG-17 are contributing to the advancement of human exploration of space, supporting our future Artemis program, as well as benefiting our lives here on Earth. If you'd like to learn more about any of the experiments you hear about today or the other work we're doing on ISS, you can visit www.nasa.gov/ISS-science or download our Space Station Research Explorer app, SSRX. Thank you.
Thank you, Jennifer. Now we'll hear from Scott Robinson, President and Chief Science Officer of MicroQuinn and Principal Investigator for the MicroQuinn 3D Tumor Investigation. Dr. Robinson is the Chief Science Officer of MicroQuinn, a startup company studying treatment for all cancers. Prior to MicroQuinn, Dr. Robinson worked for 7 years in investment banking, moonlighting as a scientist to fund MicroQuinn's drug discovery. Very interesting story, Dr. Robinson. Over.
Fantastic. Thank you so much. I'd just like to start off by saying a huge thank you to obviously ISS and NASA, but also to Bioserve, CASIS, and Boeing, who've supported this financially or otherwise for making all this happen. So thank you very, very much. MicroQuinn itself has developed drugs that essentially regulate the whole cell's environment, but also how that cell behaves in different disease states. So essentially that type of behavior is what we call cell signaling. Now, this regulating the whole environment, this is actually a very unique approach to cancer treatment, as the cancer environment is extremely toxic. And this is due to a variety of things that the cell that the cancer does that induces a self-induced toxicity like extra acidification and so forth. Which really brings me to my main 2 goals of the work that we're doing on the ISS. So firstly, we all understand that cancer is caused due to multiple mutations that change the behavior of the cell that enables it to grow uncontrollably, and so it becomes cancerous. And obviously, pharmaceutical companies are trying to make drugs that try to stop the cancer acting that way, to stop it or limit it from this uncontrollable growth and really get that behavior under control. And so they're looking at these signaling pathways, these behaviors, essentially, that are very important in cancerous cells. But unfortunately, there are thousands of events that are happening inside a cell at once. So how do you know which events are important and which ones are really kind of background noise, if you want? Well, what scientists discovered on previous ISS missions was that actually cancer cells behave very differently in microgravity compared to cancer on Earth. In essence, these cancerous cells showed that these signaling events that we thought were very important in cancer were either stopped, were either slowed down, or that new events actually happened. So what's interesting here is that even though a lot of the cancer's behavior changed, the cancer cell still remains cancerous. So by going into space, we can actually do a comparative analysis to the cancer's behavior on Earth and then the cancer's behavior in a microgravity environment and say, well, what behaviors have changed? How have they changed? What behaviors have stayed the same? And fundamentally here, what we can do is look at those behaviors, see what has stayed the same, and then essentially those behaviors are obviously key in what make cancerous cells cancerous. But also we can look at those changes, and because of those changes, we can say, well, how is it adapting to this new environment, this microgravity? And by understanding those behaviors, we can have a look at all this data together to then start to create new treatments that maybe target more key pathways in cancerous cells. But also we can look at better designing new therapeutics or modifying existing strategies that can maybe better account for those changes in behavior, which really bring me to my second kind of point of this mission. And that's really, microquince therapeutics themselves are really quite revolutionary in how they're treating cancer because we can regulate the whole environment and we can do it very specifically. But the issue when you're making drugs or new therapeutics is that the models we use in a laboratory setting on Earth, they're not great at replicating how cancer is inside the body. Basically, inside a human, you would get a kind of 3D tumor growth, where in a laboratory setting, there's just these two-dimensional monolayers of cancerous cells. Now, this may not sound significant, but actually, this changes everything. It changes the drug penetration properties. Also, when you think of a 3D cancerous ball, the cancer cells in the middle of that tumor, they're acting very differently. Their behavior is very differently to the cancer cells on the outside. And so really what we can do is say, right, well, in a microgravity environment, we actually get a really nice three-dimensional tumor forming. That's not true on Earth. Essentially, what we can't do is we can't really recreate that 3D tumor on Earth very well. There are ways around it. We can use scaffolds. But if you use a scaffold, it's still 2 dimensions. It's just now looking like it's 3D. But also, I said the behavior changes in a 3D tumor, and it does. So really, we can actually look at that in microgravity to get a really good representation of how these drugs are penetrating into the tumor, how that's changing the behavior of the cancer, and ultimately how that's actually hoping to create new treatments or improve the drug properties that we have for our therapeutics to better improve the outcome for patients. Essentially, I'll stop there and I'll open up to any questions.
Excellent. Thank you. That was very exciting to learn more about your research. We will now go to reporters for questions for Dr. Robinson. Please press *1 on your phone to be entered into the queue and identify to whom you're addressing. Also, your name and affiliation would be amazing. Julie, do we have any questions from reporters?
I'm showing no questions at this time.
Okay. Dr. Robinson, this project will involve breast and prostate cancer cells. Will this data from this project only be applicable to those cancer types?
No, that's an excellent question. So no, in theory, this data that will generate on the ISS, this is applicable to a lot of different cancers. So in previous missions, there haven't just been breast cancer or prostate cancer cells go up to the ISS. They've actually been lung, ovarian, and other different types of cancer. And in each case, they've noticed these behavioral differences, these changes in the cell signaling. So the data that we generate here will actually have applicability across other cancers, but more so because also, as I said, microquince therapeutics, they're very, very unique because we can modulate the whole cell and its environment. And so that target that we're actually going for is found in all cancers. It's significantly overexpressed because it's so important to allow the cancer cell to overcome its own self-induced toxicity, its own self-induced stress. So really, this data can be applied well beyond just the breast and the prostate cancers that we're looking at. And essentially, microquince therapeutics are applied to every cancer that we've assessed at the minute. So this data will be great for us to create, hopefully, a a great treatment for a lot of different cancers out there.
Okay. And is there a broader application of microquinn's research beyond cancer? I think you answered.
Yeah, I mean, that's a great question as well. So the data that we're going to generate is not just actually for cancerous cells, it's actually for healthy cells as well to some extent. So we are sending healthy cells up there. But all of this really comes back to microquinn's core target. It's a target called TIMBIM6. And this target, as I said, it's really important in the cell's environment. And a lot of disease states are essentially just abhorrent environments. They're things that go wrong. If we take something like traumatic brain injury, it's a perfect example. Upon the primary event, so you bang your head, oh, it really hurts, but you've got loads of oxidative stress going on. That's an environmental change. You have a lot of things called excitotoxicity. That's changes in the calcium signaling inside a cell. Again, all of these are changes in the state of the cell, in the behavior of the cell. So really the data we generate up there will also apply on Earth, because we can start to look at our target and look at how those changes are happening and how they're happening in healthy cells and saying, ooh, is there something we can do around oxidative stress or around calcium signaling? So there's definitely a much broader application than just cancer alone.
That's great. And just so you know, and I think you already covered this in your intro, Chelsea on Twitter says, this is amazing. And then she asked about why are you doing it in space versus not in a lab, and you covered that in your intro. So thank you very much, Dr. Scott Robinson.
Thank you very much. Thanks for your time.
All right. Thank you. All right. As a reminder, public, please submit questions for our speakers using the hashtag AskNASA. We will be happy to ask our speakers live. Next, we'll hear from Kevin Takata. He's the principal investigator for the hydrogen sensor technology demonstration. Mr. Takata works in the Environmental Control and Life Support Systems Development Branch at NASA's Marshall Space Flight Center in Huntsville, Alabama. He is a systems engineer for the International Space Station Oxygen Generation Assembly. He has worked for over 20 years on life support systems. Over to you, Mr. Takata.
Okay, thank you very much. I'm excited to be here. So first, I'm going to talk about the Oxygen Generation Assembly, or OGA, and then I'll lead into the Hydrogen Sensor Technology Demonstration, or H2ST. So I'll be talking about OGA and H2ST. So first, the OGA is a system on board the space station. It's been on board for about 14 years. It produces oxygen for the astronauts to breathe. Each astronaut requires about 2 pounds per day of oxygen. So that's how much oxygen we have to generate every day. So the OGA has been operating on the space station for about 14 years, very reliably. It's generated over 24,000 pounds of oxygen. The OGA is a unique system. It has several hazards. It generates hydrogen, it generates oxygen, and it's connected up to space vacuum. So the OGA electrolyzes water that's been reclaimed from wastewater aboard the space station. Water is electrolyzed to form both hydrogen and oxygen. And the oxygen is sent out to the cabin for the astronauts to breathe. And then the hydrogen is typically dumped overboard as a waste product. So over those many years of operating the OGA, we've learned several lessons. And so we want to do some targeted upgrades. So one of those is the hydrogen sensors that are in the OGA right now. Overall, they're very reliable, but they are a little bit finicky. They do have a limited life of about 7 months, so every 7 months we have to put a new one in. And it does require some crew attention to make sure they're operating safely. So we're looking for a replacement for these hydrogen sensors that should be more reliable and requires less crew time and can be installed for a period of years. So we've been testing some sensors on the ground, and we think we're ready to test some of these replacement hydrogen sensors on orbit. So moving on to our H2ST technology demonstration. It's essentially the size of a briefcase, and we'll be installing that in front of our OGA rack and connecting it up to our OGA's oxygen outlet port. And so it will be continuously analyzing our product oxygen before it gets sent out to the cabin for the crew to breathe, and it'll be looking for any traces of hydrogen. We plan on operating our H2ST for about 3 years. So the H2ST consists of 4 of these new hydrogen sensors within it. It consists of a flow meter so we can understand how much oxygen is flowing, and then also an electronics box to read the hydrogen sensors and send that data back to the ground in real time. So on the ground, we'll be continuously looking at the data coming down and comparing it to what we expect. We expect not to see any hydrogen in the product oxygen. Every 90 days, we're going to have the crew perform a drift check or health check on these sensors for us. We're flying up 1% hydrogen in air in bottles, and we'll have the crew connected up and flow it through our sensors and make sure that they're healthy and they respond as we expect to. Last thing I'll mention is that we haven't ever had a hydrogen leak in our system, but we want to avoid any mixtures of hydrogen over 4% in oxygen. That's considered flammable and dangerous. So our system automatically shuts down if there's 1% hydrogen in oxygen or greater. So that's the hazard that we're trying to avoid. And with that, I'll take any questions. Thank you.
Thank you, Mr. Takata. Again, for reporters, please press *1 to be entered into the queue if you have a question for Mr. Takata. Julie?
We did have a question from Mark Crow with Aviation Week and Space Technology. Your line is open.
Yes, thank you very much. If on a long duration deep space mission, what sort of resource does this technology become in terms of lowering the amount of mass on the mission and recycling? Does it save you save the mission a lot of mass in the start of the mission and then as it proceeds?
Yes, a great question. Yes, so the hydrogen sensors that we have now have to be replaced about every 7 months. So we need a new one about every 7 months. And I think the package weighs about 20 pounds. So every 7 months you need replacements and then backup spares, so that these sensors should last much longer than that. So that's part of the reason for this technology demonstration, is to understand how long they'll last, hopefully for periods of years. And also we should be able to recalibrate them on orbit, so that'll greatly reduce our spares and logistics, both on the space station and on any deep space mission.
Thank you, Mark. Julie, do we have any other questions from reporters?
I'm showing no further questions.
Okay, Mr. Takata, we have another follow-up question. Are you looking at other types of sensors for the oxygen generator assembly?
Yes, yeah, good question. So, over our years of operating, we've learned some lessons. Some of these sensors are sensitive to gravity. Some of these sensors drift a little bit more than we want them to, so we're looking at different pressure sensors as well as these hydrogen sensors. We're looking at different valves that may be more reliable. So, yes, so we are looking at other sensors as well.
Excellent. And just one question for those who are familiar with our Artemis on, return to the moon program. Do you see this technology potentially being used in the future for one of those missions?
Yes, most definitely. We do want to use our OGA on deep space missions, and because it's a regenerative system that's much more efficient than flying up large tanks of oxygen. And so we definitely want to use the OGA on future lunar missions or Mars missions, as well as these new hydrogen sensors.
Thank you. And we may have a Twitter question for you, and we'll save that till the end. Okay, Mr. Takata, if you can stay on the line.
Okay, thank you.
We'll get to our other speakers. Thank you so much. All right. Next, we'll hear from Dr. Leah Arvani-Tidu, who leads research and development for the Colgate Skin Health Group, which includes science-backed skincare brands, PCA Skin, and Filorga. Over to you.
Thank you. It's so good to be with you on the phone today. What I was thinking is that I realize I'm the only woman on the call, which is actually notable, especially in the eve of us celebrating tomorrow the International Day of Women and Girls in Science. So there are a couple of things that I would like to share with you. First and foremost, the experiment aboard the ISS illustrates PCA's commitment to science and new product innovation. Our goal is to gather new data on skin biomarkers behind changes that occur to the skin while in a stressful environment such as microgravity. We believe that the findings will help us better identify areas for early intervention in skin health and ultimately help guide the development of groundbreaking skincare innovations across all of Colgate-Palmolive's skincare brands, PCA Skin, but also EltaMD and Filorga. Colgate's partnership with ISS, but also CASES and BioServe will further PCA Skin's legacy as a results-driven, professional-grade skincare company that is deeply rooted in science. If you are wondering why ISS, changes in skin comparable to those in the normal aging process on Earth, such as skin thinning or dry, flaky skin, or even skin that is susceptible to cuts and bruises,
And it's still not
if you're
getting any audio.
You're coming
you're
through clear through the I'm sorry, you're coming through clear through this end.
If you are listening on nasa.gov/live, we're having a couple of technical issues. Please give us a moment.
Okay, and I think we have the audio corrected now.
Okay. All right, I think I'm hearing that we're all good to go. Apologies, Miss Leah. I'm not sure where we were cut off, but if you are able to perhaps answer some of our questions, perhaps that will be a great introduction to your investigation. And we do have a question for you from Twitter. Is there a link between gravity and skin health?
The link that we find between gravity and skin health is that what we are trying to learn in the conditions of microgravity is really under stressful environments. What is expected is that it will induce the release of biomarkers that they are indicative of tissue stress and tissue recovery. Microgravity is a stressful environment. We know this from the astronauts, and we know what they have told us, that there are negative effects not only on skin, bones, eyes, but also on the skin. As I mentioned in my introduction, thinning of the skin, dry skin. Now, these same effects are also observed here on Earth during the normal aging process. What microgravity will give us is the accelerated view of what takes longer time to happen on Earth.
That's excellent. Thank you. And just a reminder that if you did not hear the earlier introduction, this is Dr. Leah Arvanitidou, who leads the research and development for the Colgate Skin Health Group, which includes Skin Back Science skincare brands, and she is discussing her investigation. So we'll continue with our questions to her. But again, if reporters have questions, please press *1, and we'll make sure that you have your questions answered. Julie, do we have any questions from reporters?
I'm showing no phone questions.
Okay. I have a follow-up question. Why did you choose the time intervals of like 1 day, 3 days for your experiment in space?
Great question. Thank you. The duration of the study aboard the ISS will be 7 days in total. And this is because of the viability of this skin cell model that we are using. We had to design it in such a way so we allow 7 days for the skin after it is grown to be transported, and when it arrives on the ISS, 7 days for the duration of the experiment. It is a time course experiment because each tissue set will be pulled out and kept frozen at -80 degrees centigrade at day 1, 3, 5, and 7, so we can study the impact of gravity and capture the biological response. In order to do this, we need to have a time course study. Now, the same experiment will be conducted on Earth as well, and when the samples from space will be brought back to Earth, we will do analysis, gene expression analysis, and we will compare the findings to those observed in the control experiment that we conducted on the ground. What we anticipate is to see earlier and more dramatic signs of tissue damage and perhaps activation of skin repair mechanisms in the tissue under microgravity. And also, we're hoping that we will see different genes also change under the microgravity environment.
Excellent, and thank you so much. And I apologize for losing on the audio. If anyone has any follow-up questions on the Colgate skin aging investigation, by all means, send those questions via Ask NASA if you're a member of the public. And if you're from the media, you can always follow up with me by email, and we'll get back to you as soon as possible. Thank you so much, Ms. Leah.
Thank you.
Okay, next we'll hear from Hidetake Okamoto. He's the Assistant Manager of Sales and Planning at the Development Headquarters of Hitachi Zosen Corporation and Principal Investigator for the Space Demonstration for all solid-state lithium-ion batteries, also known as Space as Lib investigation. Okamoto-san, go ahead, please.
Thank you for the introduction, and good afternoon, everyone. I'm Hidetake Okamoto from Hitachi Zosen Corporation of Japan. Hitachi Zosen is a Japanese machinery and plant manufacturer that manufactures environmental equipment, factory equipment, industrial machinery, power generation equipment, and so on. We will give you an overview of Space as Lib. The old solid-state battery we have developed is registered as a trademark under the name ASLIB. JAXA and Hitachi Zosen decided to conduct a demonstration experiment for the practical use of all solid-state lithium-ion batteries in space. All solid-state lithium-ion batteries are made of flame-retardant solid materials completely. Hitachi Zosen has developed an original manufacturing method that has successfully created an all-solid-state battery without the mechanical pressure conventionally used during charging and discharging. ASLIB has three main features. The first is high safety. ASLIB doesn't use liquid materials, so there is no risk of liquid leakage. In addition, ASLIB doesn't use flammable liquid like conventional lithium-ion batteries, so it does not generate flammable gas. It can be expected to ensure the safety of astronauts. The second is wide operating temperature range. The solid materials used in ASLIB does not evaporate at high temperatures, so ASLIB can be charged and discharged repeatedly even at 248 degrees Fahrenheit, where conventional rechargeable batteries are difficult to operate. Also, the material used in ASLIB does not freeze even at low temperatures, so ASLIB can be discharged at minus 40 degrees Fahrenheit. This battery can be expected to operate even in harsh temperature environments such as the moon. The third is that ASLIB can be used even in a vacuum environment. ASLIB contains almost no volatile components inside, and it expands very little under vacuum environment. Therefore, it can be used even in space. In this space demonstration experiment, we will check whether ASLIB can operate in a harsh environment.
Next part, I will talk about space experiment. My name is Fuse. I'm a JAXA engineer, and I'm coordinator for this project and working for realizing this space experiment. Since 2016, we JAXA and have been conducted joint research project with Hitachi Zosen company, and for applying all solid-state batteries to space as an important technology for space exploration. This time, as a technology demonstration mission of all solid-state lithium-ion batteries, we decided to conduct a space demonstration in the ISS exposure environment. After launch and installed of space asleep and installed on the interface system in Kibo by astronaut, and this equipment will be attached to the exposed facility on IS by robotic operation. After that, the experiment operation to confirm the charge and discharge performance in various environments on the orbit will be carried out for more than half a year. After the end of the experiment, space asleep is removed and returned on the ground for battery evaluation. JAXA aims to apply this technology to space exploration mission where more severe temperature environments are assumed. And it is also expected to be used on the International Space Station due to its high safety. We are very excited to have this new technology demonstration. Thank you very much. Any questions?
Thank you. Excellent. Oh, excellent. Again, we will now take questions from reporters on this investigation. Please press *1 to be entered into the queue. Julie, please let us know if we receive any questions from reporters.
I will do. Thank you.
Okay.
I'm showing no questions at this time.
Oh, go ahead.
I apologize. I'm showing no questions at this time.
Okay. And you got a question from Samarth on Twitter, and she asked, or this person asked, what different behavior could the battery technology show in microgravity that would make it safer down on Earth?
This technology is safer not only for ground but also microgravity environment. Same feature this technology has.
Thank you. And how could the technology improve life on Earth or for future space exploration?
Thank you for the question. Conventional battery is difficult to operate the devices that are used in high temperature, low temperature, and vacuum environment. But it is possible by our battery, so it may be made unprecedented new devices to use in such a special environment. For example, industrial equipment, medical equipment requiring higher temperature sterilization, and so on. And in space, battery temperature control can be reduced by using our battery, which makes it possible to contribute to the miniaturization and weight reduction of equipment used in the space environment and the reduction of power consumption. Thank you.
Thank you for.
Yeah.
Oh, sure. All right. Thank you very much. We can always have additional questions from the public. Again, use hashtag AskNASA, and you can follow up on with questions for any of our speakers at the end. Next, we'll move on to Dr. Bob Morrow, Sierra Space Principal Scientist. Dr. Morrow has degrees in horticulture and botany with an emphasis on controlled environment, plant growth. Dr. Morrow, can you tell us about your X-Roots investigation?
Sure, thank you. So good afternoon, everyone. And the Exposed Root On-Orbit Test System, or X-Roots, is a technology demonstration that incorporates a unique root module designed to provide delivery and recovery of nutrient solution to plants. Essentially, it's using aeroponics and what we call ebb flow nutrient film hydroponic techniques that are being modified or are modified to function in microgravity. The X-Roots technology demonstration is part of a long-term effort to make it feasible to use large plant growth systems in space, primarily for future hybrid life support applications. Examples of this would be, say, a vegetable crop production system for crew diet supplementation, both for variety and for nutritional purposes, but also for crew recreation and to assist in atmosphere and water revitalization or recycling, the environment, using the plants to take up carbon dioxide, produce oxygen, and to purify water. These modified hydroponic systems, we believe, are going to be significantly more mass efficient, safer to use, and easier to maintain in space vehicles and habitats than a soil-based type growing system as currently used in ISS plant growth systems. X-Roots itself will be mounted in an express rack and use one of the two veggie plant growth systems that are already on the space station to provide lighting for the plant growth. And incidentally, the veggies that are on ISS were actually developed by Sierra Space. X-Roots uses a reservoir and a fluids module, which contains a set of pumps and valves to spray or flow nutrient solution into each of 4 plant root modules, and to remove the fluid movement in and out of that module to control that in microgravity. We can't just use gravity to drain, so we have to use other systems to do that. Seeds will be placed in cartridges that are in a what we call a root-shoot interface used to cover those root modules. We'll be looking at a variety of different salad crop species. Examples would include leafy greens like Mizuna and various lettuce varieties, and a number of these have flown previously in veggie, but also other vegetable crops like radish, cherry tomato, and carrot. If all goes as planned, the crew will conduct a set of 4 planting and harvest cycles, and we will take care of operating the actual X-Roots payload as far as setting the parameters for the hydroponic systems from the ground from our payloads operations center. Variety of plant species that will be that we're flying. We're flying a total of 16 different types, but several of those will just be used for germination studies, while several others will be grown through a standard production cycle. Cameras will be used to collect the images of the root and shoot growth and to collect video of the fluid behavior in the root modules. This is kind of a combination both of a fluid physics test as well as a plant growth test. We'll be looking at the interaction of the nutrient solution with the plant roots and with the hardware systems, seeing how well the various plants germinate, as well as looking at root and shoot growth rates and general plant development. Our ultimate goal really is to answer questions needed to refine both hardware configurations and operating protocols that will allow us to feasibly scale up our space-based plant growth systems for future applications such as Mars transit or cislunar type of habitats and so forth. So with that, I'd be happy to take any questions.
Thank you so much, Dr. Morrow. This is great. You got a social media question as well. Joseph on Facebook asked, how do the plants know which way to sprout with no gravity?
Well, basically they don't, but what we can do is plants orient towards blue light. So in the absence of gravity, by making sure we have a source of blue light in our light cap, the plants will orient towards that. So that controls the upper part of the plant. The lower part in the root zone tends to grow into the wet area, so it'll want to grow down into where the spray is, but it's also got a cover, and so they're kind of entrained down in that area. So we're really imposing a cultural control to get the same kind of plant format you would see on the ground.
Okay, great. We got another question for you. Why is it important to view the plant growth on video and/or images?
Well, this is really the first time that we've been able to grow large roots in space without having a growing media. So this will allow us to really understand the root development and how these fluids interact with the roots. And really the only good way to get that information down is through imaging. There's not a good set of sensors we can use to do that. And, there's not enough crew time that they can go in there constantly, opening it up and looking at the roots. So it's just much easier to get images and video and send those down to the ground for evaluation on how well the system is functioning.
Sounds good. Can astronauts sample the foods grown in this way?
Well, they've sampled some of the food grown in the veggie, but this experiment so far is not, there's not a plan to have the crew eat it. There's, other issues that have to be, accounted for, like microbiological safety and so forth, that were not really part of this payload demonstration. So, but ultimately this will lead to food, to crops that the crew can eat. Mm-hmm.
Excellent. Thank you, Dr. Morrow. Okay, Julie, do we have any questions from media or any of our speakers?
I'm showing no phone questions at this time.
Okay. If there are no more questions, we will take care to answer any additional questions from using the hashtag #AskNASA. Reporters can also follow up via email to me, Gina Anderson. My email is Gina, gina.n.anderson@nasa.gov. Thank you for your interest in this important science, research, and technology that we're launching aboard Northrop Grumman's 17th cargo resupply mission to the International Space Station. You can follow all the research being conducted during the Expedition 66 mission by visiting nasa.gov/station-research-news or following @ISS_research on Twitter. Please be sure to tune in next week, Friday, on nasa.gov/live for our pre-launch news coverage. We'll hear from the International Space Station Program, Northrop Grumman about the Cygnus spacecraft and Antares rocket, and receive weather updates prior to launch. As a reminder, you can listen to a replay of this teleconference by dialing 866-453-1997. Again, that's 866-453-1997, or you can visit the NASA video channel on YouTube. Thanks, everyone, for participating in the conference. We look forward to we do have a question. Apologies.
Yes. That's one moment. Our question comes from Mark Carreau with Aviation Week and Space Technology. Your line is open.
Great. Thank you very much. My question is for Dr. Robinson, if it's still possible to ask him one. And if so, my question would be how the treatment therapy that they're developing might be administered to a cancer patient.
Hi, yeah, absolutely. Thanks for your question. So actually, we've come up with a couple of different types of therapeutics. In the first instance, we made something called peptide therapeutics, which would have had to have been given through intravenous injection, so how you would give chemo. But right now, we've actually got small molecules, and we've got some great lead candidates, and we've managed to make them so that you can take them in pill format. So at the minute, we've actually done some fantastic in vivo studies that have shown that the tumor growth within a 1-month time frame can actually be reduced by anything from 70 up to 90% by taking these tablets. So at the minute, we're going to be progressing our small molecule tablets into a clinical setting in the near future.
Thank you, Mark. Do you have any additional questions from reporters?
I'm showing no further questions. Thank you.
Okay. We did get another question, and I apologize. Apparently there are lots of interest on social media as well, so we're trying to capture them. And this is going to be for Dr. Morrow, I believe. The Virginia Spaceflight Academy on Twitter asks, how long is a full growth cycle for the veggies and how many different types?
Sure. That's a full growth cycle for leafy greens and things like radishes tend to be about 30 days. And I think that'll be close even on orbit based on previous plant growth experiments. We have a total of 16 different types of seeds we're flying. And in addition to what I had previously mentioned, that will include things like Japanese salad turnips and dwarf wheat, and it's not really vegetable, but be flying that. And then we have Chinese cabbage. We have multiple varieties of some of those too, different, just different cultural varieties. The things like tomatoes, that would probably be more like 60, 65 days to fruiting. Mm-hmm.
Thank you, Dr. Morrow. And we have another question. I believe this is going to be for Mr. Takata, if you're still on the line.
Yes, go ahead.
Okay. Jean on Twitter asks, will your technology be used on the Lunar Gateway if successful?
Yes, correct. That's the plan. We're looking at various upgrades to our existing oxygen generation assembly, and one of those would be the hydrogen sensors. If our tech demo proves successful, then yes, we would integrate that into a future oxygen generation assembly for the Moon or Mars missions.
Excellent. That's great. And we're going to close out the questions for our speakers. Again, thank you for participating in our Science Highlights Media Teleconference. Again, the important science, research, and technology that's launching on Northrop Grumman's 17th cargo resupply mission to the International Space Station is something that we'll discuss quite a bit until launch next Saturday. Again, please be sure to tune in next week, Friday, on nasa.gov/live, same link here, for our pre-launch news coverage. We'll hear from the International Space Station program, Northrop Grumman, about the Cygnus spacecraft and Antares rocket, and we'll receive weather updates prior to the launch. Again, as a reminder, you can listen to a replay of this teleconference by dialing 866-453-1997. That's 866-453-1997. And of course, you can also watch on NASA's video channel on YouTube. Thanks, everyone, for joining us, and have a great day.
Thank you for your participation. Participants, you may disconnect at this time.